So let's next start the exercises. In this first one, we have to verify the claims in example 12 to 8, which we may not remember. So here is example 12 to 8. Here we have any set X on which we have the discrete metric D disk, so that the pair consisting of X and this metric is a metric space. And we have a subset E in X, then these are the claims. Every point of E is an interior point of E. Every point in the complement of E, that means every point outside of E, is an exterior point of E. And the boundary of E is empty. Let's now verify these claims. The solution is pretty straightforward. So we first take any point X in E. Because the metric is discrete metric, we know that the ball centered at X having radius 1 is the singleton set consisting of X, and which is a subset of E because X is a point in E. And that is how any point in E is an interior point of E. And next we take any point outside of E, that means any Y in the complement of E in X. And you can again consider the ball centered at Y having radius 1. This one also is the singleton set consisting of Y. This time, however, because Y is lying outside of E, this is disjoint with E. Its intersection with E is the empty set. And so by the definition of exterior points, Y is an exterior point of E. So any point inside E is an interior point, any point outside E is an exterior point. So that leaves no room for any other type of point. And that's what we write next. Since any point of X is either in E or in its complement, so there is no boundary point of E. So that's why the boundary is empty. Next, exercise 2, where we have to prove proposition 12 to 10. So let us first recall the statement. So I have written things briefly because we just need to recall what the things are. So we have a metric space X, D in which there is a subset E and a point X0. Then the following three statements are logically equivalent. If any one of them is true, then so are the other two. The first statement is that X0 belongs to the closure of this set E. That means X0 is an adherent point of E. The second one says that X0 is either an interior point of E or a boundary point of E because it belongs to their union. Their union means the union of interior of E and boundary of E. And the third statement is that there exists a sequence Xn in E, which means that all the terms of this sequence are points in E that converges to X0. So we have to prove that A, B and C are logically equivalent. So let's do that. Let's start the solution by taking X0 in the exterior of E. I know that we do not have anything to do with the exterior, but let's see what happens if we assume X0 inside the exterior. By the definition of exterior, then some ball centered at X0 will be disjoint with E, will not intersect E for some positive real number R. But then this equation implies that X0 does not belong to the closure of E, or in other words, X0 cannot be an adherent point of E. Why? Because by the definition of adherent point, if X0 has to be an adherent point of E, then all balls centered at X0 have to intersect E. This ball, however, is not like that. So that's why X0 does not belong to the closure of E. So what have we shown? We have shown that if X0 is an exterior point of E, then X0 is not an adherent point of E. Note that it's an if-then statement, that means an implication. So having this statement true is the same as having its contrapositive true, because an implication and its contrapositive are logically equivalent. What is the contrapositive? The contrapositive is that if X0 is in E bar, in the closure, then X0 will not be in the exterior. But what is the exterior of E? It is the complement of the union of interior and boundary. That is because any point in your space is either an interior point or an exterior point or a boundary point. So this means that if x0 is not an exterior point, then it is either an interior point or a boundary point. That is why in place of this thing, x0 not belonging to exterior of E, you are equivalently writing that x0 then is either in the interior or in the boundary, that means in their union. So you have ended up proving that if x0 is in E bar, then x0 is here, or in other words, that statement A implies statement B. So we write the conclusion of this part that A implies B. Next we want to prove that B implies C. So we assume B, that means now x0 is either an interior point or a boundary point. Let us first see what happens if x0 is an interior point. If x0 is an interior point, then automatically x0 is after all a point in E, because we have already seen before that the interior of a set is contained in itself. But then the constant sequence, all of whose terms are equal to x0, that becomes a sequence in E, and which of course converges to x0. That's what we want, right? We want a sequence in E converging to x0, and we have got that sequence in this case where x0 is an interior point of E. So next we have to see the other case, that in the case where x0 is a boundary point, then also we need to generate a sequence that will be a sequence in E and that will converge to x0. So next we consider just that case where x0 is in the boundary of E. But then being a boundary point means what? It means that if you take any ball centered at x0 with whatever radius, that ball intersects both E as well as the complement of E. In particular, we are going to concentrate on those radii that are reciprocals of positive integers. For any positive, you can write it more clearly here, okay, more explicitly. Then for any positive integer n, I have simply written n greater than or equal to 1. The ball centered at x0 having radius 1 divided by n in particular will also intersect E, that means the intersection will be non-empty. Alright. Now what do you see here? You see here a collection of infinitely many sets. Those sets are these intersections, and I say infinitely many because for each positive integer n, you have one intersection. So you are looking at a collection of infinitely many non-empty sets, and that is why you can apply the axiom of choice here and choose one element from each such intersection. But how many such elements will you have? As many as you have positive integers. So those elements will give you a sequence. So that's why we write by the axiom of choice, there exists a sequence xn such that xn belongs to this nth set for all positive integers n. Now what is the consequence of all these things? The consequence is this. Then our sequence xn is a sequence in E such that this limit is equal to 0. The limit of the distances dxn, x0 as n approaches infinity is equal to 0. So by the definition of convergence, this sequence xn converges to x0. Now let us see what really went on here. Why is xn a sequence in E? That is because each xn belongs to this intersection. So in particular, it's in E as well. That is why xn becomes a sequence in E. But how are we getting this? Where are we getting it from? We are getting it from the fact that xn belongs to this ball. What does that give us? It tells us that the distance between xn and x0, this distance is less than 1 divided by n, right? Because that's the definition of ball, open ball. But at the same time, these distances, you can imagine here, this distance, forget about this limit equal to everything, just this distance is strictly less than 1 divided by n. On that side, it is greater than or equal to 0 because all distances are non-negative. Alright. Now, as n approaches infinity, 1 divided by n converges to 0. And that sequence on that side, which is constantly 0, also converges to 0 as n approaches infinity. Those two sequences, on this side the constant 0 sequence, on that side the sequence 1 divided by n, they approach 0 as n approaches infinity, and this sequence is trapped between them. So by the comparison principle for limits of sequences of real numbers, this sequence should also converge to 0, and that is how you have this. And that's how, again, in this case also, you have found a sequence of points in E which converges to x0, and that's how B implies C. So now all we have to prove is that C implies A. So finally we assume the statement C. That means let there be a sequence xn in E that converges to the point x0. Now what is it that we have to prove? We have to prove that the statement A is true. That means that x0 is an adherent point of E, that it belongs to the closure of E bar. So we choose any epsilon greater than 0 because xn converges to x0. From this convergence, there exists a positive integer n such that the distance between xn and x0 is at most epsilon divided by 2 for all indices n greater than or equal to n. That's the definition of convergence. In particular, if you choose small n equal to capital N, also this inequality is going to be true. So dx capital N comma x0 is less than or equal to epsilon divided by 2, which is less than epsilon. So what does that mean? It means that the distance between xn and x0 is less than epsilon, or in other words that xn belongs to the ball centered at x0 having radius epsilon. However, xn, x capital N, is an element of E, a point in E. All the xn's are points in E because the sequence is a sequence in E. So that's how you have found a point in E which belongs to this ball. So the ball intersects E. So we have ended up showing that no matter what our epsilon is, the ball centered at x0 having radius epsilon intersects E. And so by the definition of adherent point, x0 is an adherent point of E, that is x0 belongs to the closure of E. But that is just statement A, so that's how you have C implying A. And that completes this solution. And let me end this video here itself. There are, I think, 2 other exercises that we will solve in the next analysis video. So see you in the next video with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.